Welcome to the fourth problem solving session of the course Fundamentals of Semiconductor Devices, NOC 24E02. My name is Amit. I'm a PhD student at ISC Bangalore. Quick summary of the first three sessions. In week one, we classified the materials in terms of their electrical conductivity denoted by the symbol sigma. Then we saw the origin of a band gap that is when you bring an huge amount of atoms together of any element, let's say silicon in this case, of a semiconductor, sorry. Then there are the orbitals overlap, and what you get is a band. It splits into two. In case of silicon, we saw that. So we call this top band as the conduction band, this was the valence band, and this was the forbidden energy gap denoted by Eg. And we also saw that the electrons can be, by shining light for instance, electrons can be made to jump from valence band to conduction band and vice versa. And electrons, if they are can jump from conduction to valence band, and in the process they give away a photon, which is the principle for light emitting diodes. And as you can recall, when I talk about, these are atomic level scaling that we are talking about, so we cannot ignore the quantum mechanics in that case. However, invoking quantum mechanics for our, let's say, for which we are familiar, mostly familiar with the classical world. So what we did was that we made a model in a Ronick-Penny model. We saw that the electron will be moving in a periodic structure, in a periodic potential, something like that. This periodicity comes from the fact that lattice in a crystal, we are having some periodicity, some repetitive structures. That's where from this periodicity comes. And we saw that this diagram that you have over here is the band, is what we call band diagram. There is another thing called band structure, which we draw in E versus K. So this is E and this is K. K is your wave vector 2 pi by lambda. There we can draw the, let's say, for a semiconductor, this is the conduction band, this is the valence band. The electronic states are here. Like, again, there will be no electronic states between this energy level and this energy level, corresponding to the Eg that we have over here. And this diagram, the EK diagram, is also known as the band structure. The curvature of this band structure, for instance, of the valence band, will give the effective mass of holes. The curvature of the conduction band will give the effective mass of electrons for any specific material. So this will be different for silicon. Silicon, anyways, it does not have a direct band gap. This, let's say, for gallium nitride, which is a compound semiconductor, has direct band gap. It looks something like this, or gallium arsenide, right? Then, so these are the energy states, but will the electrons occupy them? It's a probability, which was given by the Fermi function. Okay, if you recall. And before that, we talked a bit about the Fermi direct statistics. That is, that there are certain energy levels, for instance here, and each energy level, it's not that only one electron can occupy there. A number of electrons can occupy, which is referred to as the degeneracies. And based on that, we built up to something called the Fermi function. It's the probability of occupation at any given energy E was given by this. Okay, there is a, I'm sorry, there is a let's say negative sign over here. So E minus EF over KT. So as you can see that when E equal to EF, the probability of occupation is half, which is the definition, one of the definitions of the Fermi level. At energy levels above EF, so this term will be positive then. E minus EF will be a positive term, and the exponential of some negative term, just a second, let me see if I'm saying this correctly. For E equal to infinity, yeah, it's fine. So just to illustrate, just put very large or very low numbers. Let's say when energy level is very small, let's say negative infinity. Excuse me, just give me a minute, I'm sorry. Sorry about that. Okay, so the Fermi function I was talking about, the if E is greater than EF, then this is a positive sign, actually, not negative. Okay, so E minus EF over KT, and for, let's say, energy is greater than EF, this will be a positive number. and this would quantity will come out to be much greater than 1, and hence the probability reduces. So if you recall, the curve looks something like this: Fe versus E if I drew. So at lower, it's at for lower energies, the expression will probability will approximately come out to be 1. Okay, it was actually E versus Fe. So for lower energies, so let's say this is the Fermi level that I have drawn here. Fermi level is somewhere over here, EF. So at high energies above EF, the probability will be very close to 0. At EF, it will be exactly equal to half. Let's say this is half, and this is the EF level. So that is the Fermi function that we saw. Then we talked in some detail. We talked about the energy states that are actually available here, which is for the density of states in a 3D system. And we saw the density of states denoted by this was square root loop proportional of the energy. The density of states is nothing but essentially a number of states per unit energy per unit volume. So that's how we define this density of states energy. This can be defined for the electrons in conduction band and holes corresponding in the valence band. And finally, the carrier concentration we had arrived by, let's say, integrating the density of states. So let's say we integrate from EC to infinity, dE Fe dE. This will give you the total electron concentration, because remember, electrons will be residing in the conduction band. So similarly, exercise can be done for holes. Then we went to the heart of the semiconductor, that is, we can dope it. We talked about the donor and acceptor levels, which can lie somewhere in the conduction band. These donors tend to donate electrons, not always. Of course, we saw the incomplete ionization at very low temperatures, let's say below 100 Kelvin or something. These, even if you dope them, they cannot give away their electron, or let's say capture an electron. So that way, you have to have a reasonable amount of temperature, and if you increase the temperature even further, we saw that the extrinsic nature breaks down the semiconductor and it becomes intrinsic. Finally, in the last week, we talked about the Ohm's law, that is the traditional V equal to IR, as well as J equal to sigma E. The same Ohm's law written in different forms. Again, this is your conductivity, electrical conductivity. And then we saw that in the application of an electric field, how do the charge carriers move? We saw there's always a scattering that is involved. Thermal motion is there at a non-zero temperature. And finally, if these charge carriers are moving under influence of an electric field, they will have a certain directionality to their motion, in addition to the random motion. And we saw that there are different scatterings that they can go through. For instance, we talked about two of them, due to the ions, which are the dopants which have been ionized. And the second, we talked about the phonon scattering, because these electrons are traveling in a lattice and it's vibrating. So we talked about that. And finally, we talked about the two regimes, that is the high field and low field regime. So this is drift velocity denoted by Vd versus, let's say, the applied electric field, E, volts per centimeter, and this is centimeter per second. We saw that for low field, V equal to this is a directly proportionality. This is a straight line, and finally it saturates at some point of time. So this is the low field regime, the left part, and that is called the high field regime, where the electric field the velocity saturates. This is the high field. And in the low field, we define it as Vd equal to mu E, where mu is the mobility. Finally, we also saw that the diffusion, for instance, whenever there is a concentration gradient, so that means on one part of you have a large amount of electrons, let's say, and in the same slab you have lesser amount of electrons. There's a concentration gradient. The electrons will flow from high concentration to lower concentration. And then we saw that how the drift diffusion, the count of counterbalance is there after a certain point of time, which ultimately is given by something called the Einstein relation, which is d by mu equal to kt by q. So d is a diffusion constant, mu is the mobility, k is the Boltzmann constant, t is the temperature, and q is the electronic charge. And then this is a concept I just talked a problem on this. For more details, I still request you to go through the professor's lectures. So that's about it. Now I'll start with the today's topic, that is the p-n junction. So till this point of time, we have been talking about these two separate entities, semiconductor, let's say. So on the left you have a p-type semiconductor. By that I mean, let's say this has been doped with acceptors. For instance, if the silicon, this will be doped, let's say boron. And on the right you have another semiconductor block which is n-type in nature. So they're separately existing. We have doped them such a way, let's say the temperature is 300 Kelvin, the dopants are ionized, so well and good. Okay, now what I'll do is I'll try to bring them together. So what I'm essentially doing is this. Let's say I somehow try to bring them together, and I have formed a junction kind of here. This is also referred to as the metallurgical junction. And just to be clear, it's not like that we in real life, it's not that we create these two blocks and bring them together. It's like whenever these materials are grown. So what they're grown is that, let's say you're growing from right to left. So what you do, you first dope, let's say, a semiconductor silicon n-type with, let's say, phosphorus, and then after a certain point of time you stop the phosphorus precursor flow, that is the reagent. Phosphorus, it's not like we add phosphorus directly to the reaction chamber. Phosphorus is in form of some compound, and we stop the flow of that compound and we start the flow of a p-type. So p-type, let's say boron, so we start the flow of a compound which contains boron. That's how it's grown. I mean, it's not to be physically move them together. For our understanding, I'm just saying that this is the metallurgical junction. Where I mean to say is the behavior changes from n-type to p-type when you move from right to left. So what is essentially happening? So let me draw it here itself. So I told you this is an n-type material. This means it will have these dopants, and I'm going to denote them in blue color. So this will be dopants over here. They'll be throughout this, and they will be ionized, because remember I'm talking about T equal to 300 Kelvin, right? And these will be positively charged. Okay, these will be positively charged dopant ions, and naturally there'll be electrons that are floating over here, which these are the electrons that are there. Okay, on the other side, when you have a p-type semiconductor, so what they will have is that they have the dopants which are acceptor types, which are shown in green here. So let's say this is something like this, and again these will be negatively charged because they have accepted an electron. Now what happens when you bring them together, you can now clearly see is that there is an excess. This is an n-type, so there is excess of electrons on the right side. There are very few electrons on the left side. In fact, the left side, the p-type semiconductor, has excess of holes, right? That's what it means, doping, extrinsic semiconductor. So what's going to happen is that these electrons that are here, these electrons which are here, let's say, sorry, these electrons which are here near to the boundary, what they will do, they'll see a concentration difference from to the other side, and they'll tend to migrate. Remember, these positively charged are fixed in lattice, they cannot move, the donors cannot move, or the acceptors. So electrons will just by the facet of the concentration gradient, they'll move. Similar thing will happen with the holes. Okay, holes I'm denoting with this purple color. So the holes which are here, let's say near to the boundary, right, they'll try to migrate from all the placements, and I'm just showing from near the boundary what is happening. So what is going to happen, ultimately a balance will be achieved. Now what you see is that this block inherently was neutral, but what it's doing, it's giving away electrons and accepting holes. So what's going to happen is, effectively situation will come like that it will become slightly positively charged. I'm denoting, let's say it becomes positively charged only in this region. Why positively charged? Because now the electrons have left and only the positive charged donors have been left behind. On the other hand, what's going to happen on the left side is opposite. That is, it has accepted the electrons, or you can say that it has given away the holes, however you may want to see. And what's going to be is that this is only the acceptors will be left behind, which are negatively charged. And remember, these regions will have very few amount of mobile charge carriers meaning electrons or holes, because they have just moved away. And what you can clearly see, on the left there is a predominance of negative charge, on the right there is a predominance of positive charge. Now it will set up an electric field internally. An internal electric field will be set up in this direction, positive to negative. Now what going to happen, now see, let's talk about one more electron which is now trying to move from n side to p side. Let's say this electron is here.
This electron will want to diffuse from n side to p side, but electric field will oppose that. That's what I'm saying. Ultimately, equilibrium will be achieved where all the system will be dynamically frozen in such a scenario. That is, the region between the dotted lines will have a large amount of dopants, and of course the background silicon, in which we had doped them, and very few amount of these charge carriers, electrons and holes. They are mobile, but they cannot move because whatever the diffusion flux is there is counterbalanced by the drift flux, and thus we say an equilibrium has been achieved. And this, what you're seeing on your screens, is nothing but a p-n junction. That is the crux of it. Electrons from n side will now migrate towards the p side, holes from p side will migrate towards the n side, and that is it. That is the complete picture. Electric field will be set up, and corresponding, if you recall, that corresponding to any electric field there is a potential. So this is also known as the built-in potential, which I'll go ahead in the next slide. So yeah, so moving on to that, now I'm just putting some nomenclatures. On the left you have p, right you have n. This is the metallurgical junction that I was talking about, this one, metallurgical junction. And what this time of what I have drawn here is abrupt junction. That is, on the left side, this square that you see is uniformly p doped, and let's say the concentration is 10 to the power 15, 10 to the power 16 per centimeter cube. On the right you have uniform n doping, which means is that it's doped with donors, let's say again 10 to the power 17 or something like that. There's an abrupt shift on the doping till this line. At this point it was, let's say, 10 to the power 15 centimeter per cube. Here abruptly it has changed to 10 to the power 17 per centimeter cube. That's why it's called an abrupt p-n junction. Another flavor is a linear p-n junction. That means, let's say the concentration here is 10 to the power 17 per centimeter cube, and let's say gradually you are coming down that is linearly you are coming down to, let's say, 10 to the power 10, which is the intrinsic concentration. And then again from here you will start from 10 to the power 10 all the way, let's say, up to 10 to the power 16. And these gradings are not decreasing logarithmically, these are increasing in linear spacing. So it's called a linear p-n junction, as the name suggests. Another flavor which you may encounter in your problems as well as in textbooks and whatnot is a pin junction. So I stands for intrinsic here. So what's happening is that p and I, the similar thing is happening, is like a p-n junction. You can see so it has two metallurgical junctions here and here. Just like this is also behave, pi also will have a p-n junction. That is, so here it has excess of, so let's see the pi junction over here. This has excess of holes, it has less amount of holes, so holes will move from left to the right and so on. You'll see a depletion region being formed here, and I'll talk about the terms in a bit more detail. Just to be clear, let me go to the last slide. This region that you see over here, there are very few charge carriers, mobile charge carriers. This means it is depleted of mobile charge carriers. This region is also known as the depletion region. Okay, and finally, one of the flavors which we will go in today's session is pn plus junctions. Plus denotes that it is heavily doped. So let's say this is 10 to the power 16, maybe this is 10 to the power 19. Very highly doped as compared to the other side. So n plus p will have p plus n will have, let's say, p of 10 to the power 19, n of 10 to the power 17 per centimeter cube. Each of them is in per centimeter cube. Some places I have not written them. For instance, here the units everywhere is centimeter minus cube. But for the sake of simplicity, I'll stick to what is the abrupt p-n junction. Okay, these, when we encounter them, we'll talk about them, but for now let's just focus. It's an abrupt p-n junction. That is, left block is p side, right block is n side, and there's a metallurgical junction in between. And as I told you, these are depletion region. So this is the depletion width w, and this is x equal to 0. The junction is at x equal to 0, and we have x equal to xn on the n side minus xp on the p side. This is the width, depletion width w. And as we told, there's an electric field. We'll also see the charge profile. The depletion is the built-in potential. These are the basic concepts that we encounter, right? How do we solve them? It's just talking about theoretically is one thing, and mathematically you can solve them by using the Poisson's equation. Del square v equal to minus rho by epsilon. V is your potential, across this region, across the depletion region. Rho is the actually this is true for, this is just from the your this is a different form of, let's say, the in electrostatics we read about this Maxwell's equation, and not going into that, but just saying this is borrowed from that. So just not true just for the p-n junctions, this is true for many of the problems in physics. Rho is your charge density, v is the electric potential, this is your epsilon, the permittivity. And there's an approximation that I'll involve, as I've been saying, that this region there'll be still some electrons which try to go from, let's say, right to left, but there's an electric field that is existing which will prevent it. But we'll approximate that. We'll say that depletion region is devoid of mobile charge. This means the carrier concentration of electrons and holes in this depletion region is zero, is non-existent. That's why it's an approximation. There will be some concentration, but we'll ignore that. Second thing, what is the approximation entails is that there's an abrupt transition. Again, you see this dotted line. I'm saying here there are no electrons, but on this side there are a large amount of electrons. Which is not realistic. So what I'm saying is that here there exists a large amount of electrons, n equal to nd, but in this part, in this region, there are no electrons. You'll say, oh, but the electrons can come diffuse from here to here. If this is, because you're saying it's 0 here and it's, let's say, 10 to the power 17 or 10 to the power 18 here. That's why the approximation. So this abrupt transition between this depletion region and, okay, this region is also known as quasi-neutral on n side as well as on the p side. So this, the region between the periphery and the dotted line, and this of course is the depletion region. So these are the two approximations that are combined, and they are together known as a depletion approximation. This because otherwise it will be very difficult to solve the Poisson's equation. So if we invoke that and then we try to solve the problem. So first, as I told you, there are multiple constructs like electric field, charge profile, how it looks like, depletion with built-in potential. We'll go into them one by one, and I'm just building up so that when we solve the problems, you'll have at least first of all a summary of it, and plus some command as to what I'm talking about. Okay, so let's first talk about the electric field that we have. So just a second. Yeah, so this is your abrupt p-n junction again. This is the depletion width that you're seeing between the, depletion region between the dotted lines, and here is your metallurgical sorry, here is your metallurgical junction. Okay, now I'll invoke what I listed in the previous slide, the depletion approximation, and let's try to depict what we mean. So what I'm drawing here is just the charge density denoted by rho as a function of x. So what is the approximation? The depletion region is devoid of mobile charge carriers. So in this region there are no charge carriers, which means there is only positively charged fixed dopant ions. Again, I'm assuming 100% ionization. And here what I'm going to assume, this will be naturally be electrically neutral. Why neutral? Because as many electrons are there will be, for every ionized dopant there will be an electron, right? Electron will be free to move, but electrically this whole region, this quasi-neutral region from here to here, this will be electrically neutral, hence charge will be 0. And Nd is the dopants over here. All the electrons have gone to the p side, let's say. So here it's only QND is left, and this is a constant QND. Q is just to, this is the number of dopants, just to get to multiply the electronic charge, you get the concentration. This will be positive sign because donors will have donated their electrons. Similar thing is happening here on the n side, on the p side, sorry. So here acceptors will have accepted the electrons, which, let's say, were coming from the n side to this. Okay, and again I am assuming there are no holes or electrons here. So all the total charge will be just equal to the charge of the acceptor ions. That's it, because there are no mobile charge carriers. And Na is the number of charge, the acceptor ions. Q is the electronic charge. The negative sign here denotes is due to the fact that these are the acceptors that we have over here. So this is what this is also known as the charge profile of an abrupt p-n junction. This time on rho versus x. This is after the depletion approximation. Please note that this is very important. how in real life, as these boundaries are not so sharp, there are many non-idealities involved, but this is a fairly good approximation. Okay, now what I told, our aim was to solve the Poisson's equation, right, which is written here on your screens. And from this, see, if you know the charge profile, right, if we know rho, we can put the rho over here and get the potential. Okay, and as I told, here we is electric field, so electric field is nothing, E equal to minus grad V. So you put over here and grad V is replaced by electric field E, and negative sign gets cancelled. So from here what you can get is just by rho, right, this is the gradient of E. So the electric field slope is given by nothing but the and your charge. So charge here, let's say on this side, let's try to solve this now. That grad E equal to rho by epsilon. So epsilon is a constant. Rho on the, let's solve this for the right side first. Okay, let's just okay, let's solve it for the left side first. So on the left side, with the P side, that is in the depletion region in P, you replace rho by this constant quantity minus Q and A, right? And then you integrate it, because this will be nothing but, so E will be nothing but integration of rho by epsilon dx, right? And when you integrate a negative number, right, what you are going to see is E will be negative first of all, right, and it will be, rho is a constant, Q and A, so you will get something like minus Q N A X. Here electric field is 0, please remember that, because in this region rho is also 0, so here the electric field is 0 on both the quasi-neutral regions. And you will see that E will start to increase as a function of x, something like this, because the electric field is this expression when you put the limits, right. So let's say from 0, um, let me just try to solve this mathematically in a proper manner. Okay, then I think it will be better to avoid confusions. Okay, so what I was saying is that if you integrate this expression, you can get the electric field. Okay, and how it comes out to be in this form. Okay, it comes out to be of this nature. Why? Because again rho is a constant on the left side, so if you integrate a straight line, if you integrate a constant, if you integrate like this, y equal to something constant c, so if you integrate y equal to c, right, y dx, right, what you will get is c times x. So integration of a constant is a straight line with some slope, so that's why you see this line. Okay, why this is sloping negative and all, now I'll go through that. And more importantly is this parameter Emax. So we'll address both the things. Here it's 0, I have been made myself clear, because the charge density is 0 and we are taking this as the reference. Okay, so I'm interested in finding the value of Emax, and secondly I know this will be a straight line, right. And so what I'm interested in finding out is what will be the value of this Emax. Okay, so let's do that. So in order to find the value of Emax, what I'm going to do is, first let's consider the left side. So I'm writing this Poisson's equation over here, where P denotes the P side, the left side. Okay, and simply you integrate it from 0 to Emax, whatever this value is. What are you going to integrate? The charge density on the P side, that is in the depletion region on the P side, over epsilon into dx. You are going to integrate it from minus xp to x equal to 0, because there only we are interested only in that region. Okay, and as I told you, I'm assuming the electric field to be 0 on the left side of this. In the quasi-neutral region there is no field. You integrate that, you'll get you will get Emax minus 0. Okay, there's an error, this is Emax minus 0. Emax minus 0 will be equal to from minus xp to 0, these will be the limits, and if integrated, rho value is nothing but minus qna, so I have taken it out, minus qna by epsilon, and you will get this value 0 minus xp. So effectively it will come out to be this, see, minus qna times xp over epsilon. This is the value of Emax. Let's do it on the right side now. That's why this term n denotes the rho n is the charge density on the in the depletion region on the n side. Again, we integrated this time from Emax to 0, let's say the value of Emax, and finally we know at x equal to x and there is no electric field because we have entered the quasi-neutral region here. So again you put the value of rho n as plus q and d, again why plus q, because these are donors. It was minus q and a here because these were acceptors, over epsilon xn minus 0, and this will be 0 minus Emax. So in order to complete, the Emax now value will come out to be minus q and d by epsilon xn. Now I just assume that they're going to meet this here. That's not necessarily true, but this has to be true to the charge neutrality, because you see Na times xp, right, is nothing but the total charge that is residing over here. The charges can, there's no way for the charges to leave the system because it's not connected to any battery or something. So whatever charge initially, all the positive charge in system has to be equal to the negative charge in the system, and we have assumed that the quasi-neutral regions, by definition, they do not contribute to any net charge. The only net charge is being contributed by this region, the depletion region on the p side and the depletion region on the n side. So all the negative charge on the p side, that will be this minus qna times xp into area, that is total negative charge, has to be equal to the total positive charge, which is qnd times xn into area. I'm not denoted the area here, but you just assume that if this is a 3D block, it will be extending in this dimension, right? I have not denoted that over here. If it will be extending, it's a rectangular block extending in 3 dimensions, it will look something like this. And this is the area A, the cross-sectional area A that I'm talking about here. So area will get cancelled, but Na times xp will be equal to Nd times xn, which is the charge neutrality. So Na times xp will be equal to Nd times xn. This is also known as the charge neutrality. And due to this charge neutrality, the Emax on P side will be equal to Emax on N side. Hence, there is only one Emax. Okay, so that is the reason, because this charge neutrality exists due to the depletion approximation, many other things that we had taken. Emax, there will be Emax that is coming of this form, right? Now let's move on to the second construct. I was talking about the built-in potential. So let me see. Let me just tell you as to what I'm talking about here. So on the P, you have the P and the N. Again, I'll try to bring these blocks together. So let's just try to recall how does the band diagram looks like. So this will be EC, this will be EV. This is a P type, so Fermi level will be closer to the valence band. Let's say EFP. Again, on the N side, you will have EC, EV, and you will have its Fermi level EFN, let's say. And when you bring them together, and in the system, as we are talking about, is in equilibrium, this is not connected to battery or something, the EF on both sides have to align. So let's bring them together. Naturally, a depletion region will be formed, which you see over here. This is a depletion region, minus xp, 0 and xn, and on the left and right we have the quasi-neutral region. Okay, so EF has to be aligned. EF has to become aligned because the system is at equilibrium. It will go something like this. So what's going to happen is that this will move up and this will move down. But in the quasi-neutral regions, the shape should not change. So let's try to put this here. Let me draw some lines for better clarity. So here is a quasi-neutral region. You see it's behaving just like this, EC, EV, and EF is close to the EV, right? Again, on the quasi-neutral region on the N side, you have EC, you have EV, EF is closer to EC, just you expect in a N-type semiconductor. So quasi-neutral region, the both sides there's nothing has changed. But when you move them together, essentially, this has at a higher energy, system will try to go down the lower. There are many ways of looking at this. So one is from the system energy perspective. The other is the fact that the electrons are traveling. So electrons are here. So they will just leave behind the positively charged, the dopant ions here, and electrons will travel here to get accepted on the p side. That is one way of looking at it. But ultimately, this is the shape of the band diagram that you will get. Okay, and interestingly, at this point of time, just at the metallurgical junction, this is the metallurgical junction over here, you see that EF equal to EI, it's as if it's intrinsic, so at this level. That's a peculiar thing of the PN junctions that we have encountered. Okay, and the dotted line here just denotes is the intrinsic level. Do not go by EF, think of it as the intrinsic level. Intrinsic level will be at the midpoint of EC and EV, hence you see it is following the curve of EC and EV. Natural question can arise is what is the equation of this curve? This is very easy to say. Why? By this, we know the electric field looks something like this, right? So how will the potential look like? You just integrate that. So integration of a y equal to mx plus c is a parabola, and this is the parabola that you see. This is a parabolic curve, which will become more clear in the next slide. Okay, but what I'm interested in finding is this potential VBI. This is also known as the built-in potential. Where does this potential come from? Just by joining the P and N junctions, this potential has arisen. Okay, so let's just try to find its value very quickly. What I'll try to do is this very simple trick that we do to find this. What I'll do is that I'll equate this energy level with this energy level. They are the same, but just the fact that on the P side and on the N side. Okay, so what is this energy level? I can write this as EC minus EF on P side. This is equal to this energy gap, that is EVBI plus EC minus EF on the N side, this gap. This total height is equal to this plus this, straightforward. Okay, now if you recall the expression of the charge carriers that we have talked about in the second session, the electronic charge concentration is nothing but NC exponential of EC minus negative of EC minus EF over KT. This is true for every semiconductor. Okay, so when you're talking about EC minus EF on P side, from there I can write that this will be equal to N on P side. I'm interested in finding this value. Okay, so NP over NC. Okay, let me just rearrange the terms. It will be easier to see them. Just a second. Okay, so I'm interested in finding this VBI term. So let's say EVBI equal to EC minus EF on N side minus EC minus EF on P side. Okay, sorry, like this term has to go that side. Okay, so EC minus EF on N side, this is written exactly over here. You see this term minus EC minus EF. This is what I'm interested in finding. This will be concentration N over NC log of this times KT. This will be minus, so again EC minus EF, but this time I'm writing only on the P side. This will be N on P side divided by NC, natural log of this, times KT. What I'm doing is that EC minus EF is nothing but natural log of N over NC times KT. This expression gives rise to this. Just take NC on the other side and take the natural log. It will be KT times ln N by NC, which is I have done here. NC and NC will get cancelled because you can write it L natural log of NN minus natural log of NC. So that will get cancelled. You will get KT natural log of electrons on N side divided by electrons on P side. N denotes concentration of electrons. The subscript denotes on which side you are talking about. So I'm talking about electrons on N side. Here it's electrons on P side. Okay. Now electrons on the N side, this will be nothing but equal to the doping, because assume 100% ionization. Electrons on P side, this will be nothing but, so remember Pn equal to Ni square. This is true here as well. So I'll write, I'm denoting everything on P side. I want to find Np. Pp times Np equal to Ni square. What is the value of Pp? Is nothing but the acceptors. The holes on P side is nothing but the concentration of acceptors, which I'm denoting it as Na. So Na times Np equal to Ni squared. From this, electrons on p side will be Ni squared over Na. Put this value here. Np is Ni square over Na. So what we get is that, I'll again use the red pen. What I have finally arrived is that Vbi equal to kT over E. E is electronic charge, let's say Q, ln NdNa over Ni squared. Okay, so built-in potential is nothing but kT over Q Na times Nd over Ni square. I'll just write it a bit more clear. And natural log of Na times Nd over Ni squared, and this level was Ev earlier. That's it. So now we have also obtained the expression for the built-in potential. Okay, and just to quickly summarize, because I believe I have established the concepts enough. So this was the, if you recall that this is the band diagram, band diagram that we get in a abrupt p-n junction. This is the charge profile that we saw. Again, note the units: coulombs per centimeter cube. Okay, it can be coulombs or per centimeter cube is true because we're talking about the density. Okay, electric field, we saw this kind of a profile. The Emax will be the same. Why that arose is due to the fact that the charge neutrality has to be respected. This was the expression that we saw of the built-in potential, and I was saying, right, this expression, the built-in potential, is nothing but this, or this, just that they've taken this to be the reference in this case. It doesn't matter, it's just the difference that matters. For instance, you take this as the reference, right? Whatever potential you are gaining is the and here this is, you see this is a drop here. That is because you're applying by the electronic charge, which is negative. So just don't get confused with the two terms. Okay, this is reducing here because you're multiplying with the electronic charge. All the things here in this diagram are energies, and energy is arrived at multiplying potential into, so energy equal to minus Q electronic charge times the potential. So if potential is increasing, this means electronic energy is decreasing, which you see over here. I told you this is a parabola. Why? Because if you integrate this expression, this is a straight line, y equal to mx plus c, you will get sum of half mx square plus cx plus d, which is a parabola, which is this form. Okay, and which is also written over here. So this is essentially the same thing that I am doing. You integrate this straight line and you'll get this expression. Okay, right. And also one charge neutrality I'll also write here. This will be Na times xp equal to Nd times xn. This is charge neutrality. This is the built-in potential. That is, if you integrate this curve, you'll get this potential. Also, xp plus xn equal to w. This is xp, this is xn, and total width is w. So what you can do is that in this expression you can replace xn and xp in terms of w using these two expressions. Okay, and you will get the depletion with the expression as this. So I'm not going to do this. This is just, I just told you the way how you arrive that. The electric field, that is the maximum electric field, this is the point E naught here, E naught or E max as I wrote earlier. This E naught or E max we saw, the built-in potential we saw, and using that, using the charge neutrality as well as the simple fact that xp plus xn is the total depletion width, what you can do is you can arrive at this expression. Okay, now let's I'll take a pause here because I'm going to enter the numerical portion. So if you want me to repeat any concept, you can just feel free to ask. Pause a bit here. All right, so let's continue now. So now in this problem we are required to find the built-in potential of a silicon p-n junction. of a silicon p-n junction where it is yeah, so nd your doping n side doping is given, your p side doping is given. Now since this is not clear, but this is an abrupt junction, not explicitly written, but you can get from this value that nd is here and na is this. If it were a graded junction it would have been written, but here it's an abrupt junction, that is it's abruptly changing from p side to n side. Okay, we are required to find the built-in potential, and we know the expressions for, just a second. Okay, so this is the band diagram, the corresponding band diagram that we have been seeing. Hold on a second. Right, so this is the band diagram, and this is the corresponding expression which we had derived a couple of slides back. So here if you just need to put in the value, so kt over q is given as 0.206 electron volt divided by the electronic charge E, or Q value is E in this case, natural log of Na times Nd. So Na value is given 10 to the power 18, Nd's value is given 10 to the power 15, Ni, the intrinsic carrier concentration, is around 10 to the power 10 for silicon. Yeah, it's given 10 to the power 10. I'm not writing Cm minus 3 because it will get cancelled, squared. So this gets cancelled, but you will get is 0.026 times natural log of 10 to the power 33 over 10 to the 20. So 0.026 ln of 10 to the power 13. So let's see what this number comes out to be. So natural log of 10 times 13 times 0.026. So this is coming out to be 0.78 volts. This is the correct answer. So this is the built-in potential for this specific Nd and Na. Now, as I have been telling you, let's not get satisfied with just putting the expression. Let's try to tweak it a bit. Okay, so here you can see that Na is greater than Nd. 10 to the power 18 is much larger than 10 to the power 15. Okay, and you get this kind of a built-in potential. What will happen if I swap these two values of Na and Nd? Will the built-in potential change? It will not change. As you can see over here, the product will still come out to 10 to the power 33. But what will change is how they look like. So in this problem, if I want to draw your charge profile, okay, rho versus x. So in this problem, what is said that Nd is 10 to the power 15, Na is 10 to the power 18. Its charge profile will look something like this. Sorry, because on the left is your P. Okay, so it will be something like this. This is your P side, and your N side will look something like this. Why? This is coming from the fact that this is your minus xp, this will be your xn. Why such charge profile? Why I'm saying this? I'm saying this because of the charge neutrality. Charge neutrality says Na times xp should be equal to Nd times xn. So xn over xp, just rearranging, will be Na over Nd. Na is 10 to the power 18 over 10 to the power 15. So xn over xp is 10 to the power 3. Huge, 1000 times. This means if xp is 1 microns, it will not be 1 microns. If xp is 1 nanometers, this xn is 1 microns. Such a junction where you have such an abrupt, such a huge change between the doping levels, this junction in fact is P plus N. P plus N. Why? Because P is very highly doped as compared to the N type. So in P plus N junctions, and this is also a P plus N junction, in P plus N junction you will see the depletion region is extending primarily to the N side. I repeat, in the P plus N junction, the depletion region primarily extends into the P side. We'll again visit this concept in the problem after this. So again, in this problem, we need to calculate. So we have been given a p-n junction. In this problem, the built-in potential is given to us. Coincidentally, the built-in potential is same as the previous problem. Okay, and only acceptor concentration is given. Okay, again this is the band diagram, and the built-in potential is, I just put the values. This is 0.026 ln, and d is what we required to find, and a is 10 to the power 17 over 10 to the power 10 into 10 to the power 10. So if I recall, this nd into 10 to the power 17 over 10 to the power 20, this was coming around 10 to the power, previous problem it was what, 10 to the power 33. Yeah, so from this you can get nd equal to 10 to the power 16 per centimeter cube. Fine, we have arrived at the answer. But this time if you see the difference between this will we usually will not call it a p plus n junction. Okay, why will I not do that? Because or sometimes people do call it, but here the concentration, the doping density is different, is not so drastic. So here this time, here n a over nd in this problem is 10 to the power 17 over 10 to the power 16, which is 10 units. Okay, in the previous problem it was 10 to the power 3. Here there will still be a difference. For instance, depletion region again will be extending a bit, quite a bit in fact, towards the n side, not as severe as the previous one. Okay, so what I meant to say by these two problems is that even though you can have the same built-in potential, the product of the respective doping levels of acceptor and donor will determine how your depletion region looks like. Okay, even though the charge, even though the built-in potential will be the same. Okay, that's the key takeaway from these two problems. Now as I've been as just I introduced the asymmetry between the depletion widths on the n side and p side, this will be more very clearly brought forward in this problem. So now we are required to find the depletion width of a p-n junction where nd and na are given at 300 Kelvin. So again, assuming 300 Kelvin, I'll reiterate that I'll assume that all the dopants have been ionized. Okay, which is a fairly safe assumption, as we saw that over 100k, this is which was, we are fine with that for silicon. Okay, now so again the band diagram you have, and we know the expression for depletion width. It's the same. I just, in the summary slide I had shown you, we had talked about this. Now what we don't know, we know Na, Nd and epsilon silicon, but we don't know is the built-in potential. Let's just find that, because we know the expression for, sorry, we know the values of these two entities, the Na and Nd, right? So let's do that. So Kt over Q is, again as from the previous problem, is 0.026 ln 10 to the power 15 into 10 to the power 19 over 10 to the power 10 into 10 to the power 10. Okay, so it will be 0.026, this will be 34, 10 to the power 14. Last problem it was 10 to the power 13 if I remember correctly. Okay, so let's find the value. So this will be ln 10 times 14 times 0.026. So this is 0.838 volts. Very good. Now let's put this value over here in depletion width W. So what you will get is 2 times epsilon silicon. Epsilon silicon is given as the epsilon naught, it's 8.85 into 10 to the power minus 14, and the dielectric constant is 11.7. Q is electronic charge, 10 to the power minus 19. Na plus Nd, so 10 to the power 15 plus 10 to the power 19, which will approximately be equal to 10 to the power 19 over 10 to the power 15 times 10 to the power 19, and finally VBI, which is 0.838 volts. This term gets cancelled. The first term, 10 to the power 19 terms gets cancelled, and what we get here now is all this mess. And let me just rearrange. 2 into 8.85 into 11.7 over 1.6, this is into 0.838, and the powers will be minus 14 So this will be minus 5 into 10 to the power minus 10. Units will be centimeters. Okay, right. So 10 to the power 15 minus 4, yeah, minus 10. Okay, so let me see what this number comes out to be. 2 into 8.85 times 11.7 times 0.838. This is 173 by 1.6. So this is 108. We'll take the square root. So this is coming out to be 10.41 times 10 to the power minus 5 centimeters. So 1.04 into 10 to the power minus 4 centimeters, or I can also say 1.04 microns. 10 to the power minus 4 centimeters, 1 micron. So this will be the correct answer. Now, this problem gives you a real feel as to what the typical depletion widths are. These are in micrometers, okay, not in nanometers, which is very severe, you can say, or very scaled, very extreme depletion widths. But 1 micron is still much smaller than the width of a human hair. Just to appreciate that, just by playing around with these dopings, we can change those values. Okay, fine, we got the total depletion width. I'm more interested in finding the ratio of xn and xp. Okay, so let me just tell you what I'm talking about. So we have this p block, we have this n block. Okay, it will have some depletion bits. I don't know what they are, where they lie, so that's why I'm not yet drawing the dotted line. What I do know is due to the charge neutrality, nd times xn will be equal to na times xp. Okay, we know that. Fine. So from this I can say, let's put these values. So 10 to the power 15 times xn equal to 10 to the power 19 times xp. This will give me that xn will be equal to 10 to the power 4 times xp, right? Right? So xn is 10 to the power 4 times xp. So this is our expression 1. Expression 2 I know is xn plus xp will be equal to w. If I put xn equal to 10 to the power 4 times xp over here, what I'll get is 10 to the power 4 times xp plus xp equal to w. You can ignore the term 1 in terms in as compared to the 10 to the power 4. This will give me xp equal to w over 10 to the power 4 approximately, right? And thus xn, if you put this here, xn will come approximately equal to w, because xp is only a fraction. It's not even 1, it's 0.1%. So what's happening is that all the depletion width, you can see xn is approximately equal to w. So all the depletion is happening in the n region. If I were to draw the depletion region, it will look something like this. And this is also very inaccurate. This is minus xp, this is 0, this is xn. Approximately all the depletion width is, all the depletion region is in the n side, which makes sense as I've hinted earlier, because this is a p plus n. Look, p is 10 to the power 19 doped. P is 10 to the power 19 doped, yeah, and n side is 10 to the power 15 doped. So this is effectively a p plus n junction. In a p plus n junction, the depletion widths, the depletion rise in the almost exclusively lies in the low doped region. So again, I can tell you the values, the actual values. So xn will be equal to 1.04 microns, xp will be equal to 0.1 nanometers, 1 angstroms, in fact 1.04 angstrom, but such is the scale. So you can see it's 10 to the power 4 orders. Where this understanding comes handy again in competitive exams, just by looking at the values of nd and na, you can get an idea of the nature of the junction. It's a p plus n junction, which you can see directly from this, and from this you can say, okay, so the depletion is lying more on the n side, more on the p side, and so on. If ND is equal to NA, then Xn is equal to XP, because you see these two terms get cancelled out. Okay, so these constructs, for instance, the charge neutrality expression comes in handy to determine the relative lengths of the depletion widths, or relative values of depletion widths rather. Okay, so I just wanted to point this out. That's a good thing to keep in the back of your mind. Right, so now we don't have a numerical per se, but we'll apply our understanding of the depletion widths into this problem. So here we are given silicon diode N plus P. Okay, so let me just a second. Okay, so silicon diode is given the N plus P, and a gallium nitride diode is P plus N. Gallium nitride is also a semiconductor which has a higher band gap than silicon. Okay, and they clarify the problems that P plus indicates heavy P doping, so on. Okay, so we are required to find what is the depletion width for respective regions, and as I've been saying that this is a typical PN junction, not a P plus N or N plus P, and this is the typical charge profiles that we get. And from this itself, what we have established is we get this ND times Xn equal to NA times XP, and we have also observed that we saw in P plus N junctions the depletion region lies almost completely towards N side. That is coming exclusively from the charge neutrality expression. Okay, in order to generalize that, so I can also say the inverse is true, that in case of PN plus junctions, depletion region lies almost entirely towards the low doped side. Low doped side here is P side. So we are given a PN plus silicon diode. PN plus, this means the depletion region will lie on the low doped side. That's for silicon, the depletion region will be towards the P side. So this is the case of silicon in this problem, right? So depletion region, so we can say depletion region for P side will have a higher width. So depletion region has lower width in N region, that is correct. Greater width in P region. So these two options seem to be correct. N width is lower and P width is greater, right, for the silicon diode. And for so lower width in P region, no, this is incorrect. Greater width in P region, yeah. So we have eliminated only one option till now. How we did that? Because we know for silicon Xn must be less than Xp. Similarly, for silicon by I mean PN plus diode. For gallium nitride, P plus N will get the depletion width will be towards the N side. So we can write Xn will be greater than Xp. Okay, so right. So for let's say this, let's check out the second half of the statement. So depletion, while depletion region has greater width in N, that is correct. So the Xn is greater than Xp, it's written over here. So this part is correct. Lower width in N, this part is incorrect. Lower width in N, this part is incorrect. Greater width in P plus, this is also incorrect. So only option, this is the one, the option A, the first option, which has true for both silicon as well as gallium nitride. So just to reiterate, this is just the understanding that we have, which is arising from the charge neutrality, and this becomes very prominent, as I told you, in case of when we have one junction N plus P or P plus N, because then you can see the depletion width almost entirely to one side. Okay, till now what we have been talking about is the PN junction in equilibrium. Okay, what do you mean by that? Now I want to disturb the equilibrium. So that first you have to understand what do you mean by equilibrium.
That means we are not applying any potential or not shining any light. This means the system, you have a p block and n block, and just let it be. Now I want to disturb the equilibrium. So there are multiple ways, but two most prominent ways. First is you apply a battery. Just apply a battery to this. It will supply electrons and holes and whatnot. So this is one way of disturbing. So one will say is, we also call this current injection. Second way is shine light. So as I just briefly touched in the last session, when you shine light, there will be generation of electron hole pairs, which will alter the concentration of electrons and holes, and thus the equilibrium will get disturbed. Okay, so that's what I mean by that. But for now, it'll just stick to the injection of carriers, and this becomes important. So the forward bias, that term I'm making, then becomes inject which carriers and where. So when we talk about forward bias, which means we inject holes into the p side, electrons into the n side. This is forward bias. Thus the positive terminal of the battery will be connected to the p side, and negative will be connected to the n side. There is another term called the reverse bias. So in reverse bias, what we do is that we connect the positive terminal of the battery to the n side, okay, and vice versa. Okay, and we'll see what I'm interested in finding is that how does this, in this configuration, the forward bias, it impacts the depletion width and the built-in potential. Okay, and they are related. For instance, the built-in potential, this is from the equilibrium one, the depletion width and the built-in potential. This is how it looks like, and this was our the band diagram that we had at equilibrium. How to identify? EF is flat on p side and n side. So here this is without bias, this diagram. I want to change the bias. So when I change, what's going to happen is that this EF will not be constant throughout. What we'll have is now, so this that's what I was saying. So here EF is flat. You can see the built-in potential. EF is flat from the p and n side, and this is just a wire. So essentially at the same potential, no bias is being applied. When I now apply a bias, now what's going to happen is that, because I applied a positive bias, so I'm injecting some holes. So essentially this will shift a bit towards the downside, and EF will shift a bit towards the top side. So these EFP and EFN are also known as quasi-Fermi levels. These are not the Fermi. I mean, concept is still the same. The Fermi levels here, we can still apply the Fermi direct statistics and whatnot, the exponential dependencies, but they are the quasi levels. Means rather than having a uniform Fermi level, which should be flat if it's in equilibrium, which you can see on the left side, here it's not the case. What I have done here is essentially broken the Fermi level into two parts. So on the n side, I'm talking about a hypothetical Fermi level, which I call the quasi-Fermi level on the p side, or EFP. Similarly, on the n side, in the bulk, I'm talking about another Fermi level called EFN. Why those arose? Because we introduced a battery. Okay, and there, why EFN shifts up? Because now it's easier to inject the electrons. Hence, this EFN, rather than being here, is shift towards the upside. And correspondingly, what we see is that the built-in potential, effective built-in potential, has reduced by an amount VA, which is exactly equal to the potential that I'm applying. Why it's happening? It's simple to understand when you see it like this. So the red lines are your sorry, the red dotted lines are your quasi-Fermi levels. So what's happening is that when you are applying, so here there is a pile up of electrons. Where are these electrons coming from? From the battery. So these electrons are ready to be injected, are ready to travel to the other side. Earlier in equilibrium, we have in this here, over here in the quasi-Fermi level, this number of electrons are only equal to Nd, the donors. Here I have a steady supply from my external source. So clearly you can see there's a gradient of now electrons. Even in here, there's a huge pile of electrons here and a huge pile of holes here. So naturally they're going to travel to the other side. It's as simple as that. It's diffusion driven. This problem is diffusion driven. Okay, just equipped with basic understanding, I'll try to elaborate a bit more on this.
Okay, using mathematically, till now I've been talking about qualitatively that what is happening. Now let's put some numbers. Okay, so the electrons on the electrons, let's say over here, I can write them as this: n equal to ni ef. This is just the same expression that we written we've seen in the second session, just that the Fermi level has been now been replaced with efn, the quasi-Fermi level. That's it. Similarly, it goes for the p side over here. Okay, EFI is nothing but your intrinsic Fermi level. Okay, it still exists, by the way. It's not that it's disappeared. It's just going through the mid band, something like this. This is your EFI, the red line. Okay, right. I multiply the both two terms just like we did earlier. So I get NP equal to Ni square. The EF terms gets cancelled. EFN minus EFP. We have seen that when we are not applying any bias, EFN will be equal to EFP, and you'll get NP equal to Ni square, law of mass action. Here, EFN minus EFP, that is a split in Fermi levels. What caused a split in this the Fermi level into quasi-Fermi levels? The applied potential. Hence, EFN minus EFP is nothing but a built-in potential. Nothing but an applied potential, VA. This entity, NP equal to Ni square, exponent of QVA over KT, is called the law of the junctions. Just because we are applying an external term VA. Again, if you want to go to the equilibrium, put VA equal to 0. You get NP equal to Ni square. Very straightforward term. Okay. So that is what we are talking about when we say that we are in a forward bias condition. Okay, and this is the important concept that primarily it is being driven by the diffusion, which I told over here. Yeah, so these electrons are being supplied to the n side, or let's say holes being supplied to the p side, which are willing to now to travel through along the length of this device. Okay, and this E is just denoting the electric field that is present. Okay, right. Another thing that you might have noticed, we'll just come to that when it comes. So you see over here the depletion width has reduced. Why? Because depletion width has a dependence with VBI. So in forward bias, as VBI was reduced, remember VBI minus VA, correct? So naturally depletion width will also reduce, which you see depicted over here. W is this, you see W is visibly smaller than this. Is the way of depicting. Mathematically that's also true. Okay, so till now, yeah, so we talked about this. Yeah, so next thing in this itself, same thing what I denoted earlier is this another way of depicting the same the flow of electrons and holes in this. So remember that just first to clear the nomenclature. So x equal to 0 is the metallurgical junction, minus xp to xn is your depletion width. So again you see the depletion approximation we are still holding true, that is there are no mobile charge carriers. You see the concentration plot is not there at all. What we have on the other hand is on the n side we have something called PNX. P means concentration of holes, subscript means on the n side. So holes on n side as a function of x, they are decreasing. As I told you in the previous diagram, there is a pileup of holes which is being supplied by the battery. They somehow travel through the depletion region. Remember this electric field that is existing over here. They pass through that and they arrive at this point. Now they'll recombine because there's a huge number of electrons that are here. Remember this is the bulk n-type dope, and hence their concentration will go on decreasing, something like this. Same happens for the electrons, that is electrons on p side. What's going to happen? There are large number of electrons over here. They'll traverse the depletion region. When they come here, they'll recombine, and you see this NPX electrons on p side. The concentration will reduce till what? NP0. This is the background concentration. NP0, that is this concentration. NP0 we derived, remember, Ni squared over Na. Similarly, Pn0, that is the holes on n side. 0 means the equilibrium or the background concentration. This will be nothing but Ni square over Nd. It will not be 0. Please remember there will be some always electrons and holes, because it still has to follow the law of mass action in the bulk regions, in the quasi-neutral regions. Law of junctions is applicable over here. Okay, right. So this is how the concentration curves of the electrons and holes look like. Now this is a very famous diagram that we have, that you must have seen in the lecture slides, in your textbooks, in your slides and whatnot. This is just an extension of this fellow. How do I come to this? So first of all, if you recall, in the last session I talked about that J total will be equal to Jn plus Jp. J is your charge density, current density. This will be equal to electrons as well as holes. And again I broke this up as Jn drift plus Jn diffusion for Jn. Similarly for holes, Jp drift plus Jp diffusion, right? This is what is happening. So this is the total current you see over here, and you see in this device itself, the current law has to be followed. Okay, that means the current cannot abruptly change. So that's why J total you will see is a constant value, but the individual components, their values start to differ. Okay, let's start from the left side. So again, just assume that the battery, the holes are being injected from this side. The holes are being injected. Okay, so, and in at the extreme left there will be no electric field, right? Because assume in the quasi neutral region, we assume that all the potential is being dropped across this, so there's nothing over here, not much is happening here. That's why you see the electron diffusion current at this point of time, there's no electron diffusion current. Okay, so all the current will be coming through here on the left side. Hole is the majority, this is the P side, and here P side and N side. So all the current which is coming due to the hole current. Okay, because electrons are not contributing to any current over there, right? Similar goes at the extreme right. So all the current is being contributed by the majority electrons, right? And hole diffusion current is very small. Okay, so let's consider this region now. What's happening here? Whatever the excess electrons that have come, because remember, electron injection is happening over here. So whatever amount of electrons which is denoted by this point will come over here, they will diffuse, because here there is a very large small number of electrons, here it has considerable number of electrons, so they will diffuse. And when the electrons diffuse, if you recall the expression minus E dp dn del n over del x, so there will be a electron diffusion current, is denoted by this line. Okay, this comes due to the fact when you differentiate the concentration of electrons on p side, you will get this. Okay, similarly you will get a hole diffusion current on the other side. Here, because the concentrations of electrons and holes is not changing, you will see the diffusion current remaining constant, right? So these are the different ways of depicting the different components of a p-n junction, how these four components just in the at the same point of time they are there inside the device itself, but we can break them down and see how they're contributing. Okay, there's a bit more mathematics involved, which I don't have the time to go through, but when you arrive at the J total by using these differentiating the diffusions, that's why you see these diffusion components, diffusion constants Dn, diffusion lengths Ln and Lp. You solve this and you get this expression. The total current density is given by this expression. It has an exponential dependence on the applied potential. Okay, and this term which you see on your this first bracket is also known as the Js, or the reverse saturation current density. Because we're talking about Js, sometimes also known as reverse saturation current, when you don't normalize with respect to the area. Okay, just this is a qualitative picture, and but now we'll be more concerned about the mathematical or the numerical aspect of it. Okay, so starting with a very simple problem here, that this problem asks us to consider an ideal p-n junction diode whose cross-sectional dimensions are given as 5 microns by 5 microns, and the reverse saturation current density is given, and we are applying a forward bias to this p-n junction, a p-n diode of 0.5 volts, and we need to find the forward current that is flowing. We simply use this expression, put in the values. So this term, this term that is over here, this has been given to us as 1 amps per meter square times exponential of VA is 0.5, KT is 0.025 minus 1. Okay, so this will come out to be 1 amps per meter square times exponential of this will be 20, I guess. Yeah, so exponent of 20 minus 1. So exponential of 20 is second, exponential of 20 is a huge number. 1 2 3 4 5 6 7 8 9 digits. Okay, so it's coming out to be 3 4 5 6 7 8 9. So this is 0.485 into 10 to the power 9 amps per meter squared. We need to find the current, so I will be equal to J total times the area. This will be 0.485 10 to the power 9 amps per meter square times the area, which is 5 microns over here, so this will be 5 into 10 to the power minus 6 squared. So this will come out to be 1.2 into that will be minus 12 9 10 to the power 1 milliamps per meter square, because it is 9, this will be minus 12, so it will be minus 3. 25, almost half of 25 is 12.5, so that's why I wrote so it will be 12 point something, 10 to the power minus 3. Yeah, so it's 12 milliamps, not per meter square because I multiplied with the area, 12 milliamps or so. This is a fairly straightforward problem where we had to just put the numbers, the values in the expression that is given to us. Again, I told you I had not gone through the derivation of this. This is a bit involved, and I think professor has derived in the video lectures. If you are interested, just go through that, please. Okay. This is an interesting problem, the qualitative aspect of it, where we have to analyze some things. Okay, so the problem asks us to consider the diodes made up of 4 different materials: gallium nitride, gallium oxide, gallium arsenide, and aluminum nitride. Right. So now, now assume that the P and N doping on the respective sides are same for all diodes. This means P doping for GaN equal to P doping for gallium oxide equal to P doping of gallium arsenide and aluminum nitride. Similarly, N dopings are same for all the 4 sides, and they are completely ionized. So this means they are contributing to the they're either accepting the electrons or donating the electrons, whatever the case may be. Now, if there is a requirement of a switch which has good on-state characteristics, so actually an ideal switch is which switch on at 0 volts. That means switch on at 0 volts and can support infinite amount of current. That's the ideal in the forward side, right? So what I mean is something like this. This is I versus V. An ideal switch will support infinite amount of current. This is the current, and when reverse biased, it will block infinite amount of current. Infinite amount of voltage. But if you look at the diode, it looks something like this. The characteristics of a diode. So this is an ideal switch, and this is a diode. So you can see that diode in some aspects is similar to this switch. That means one of the applications of a diode is in the form of switch, which is actually so here. But we are making switches or PN diodes, PN junction diodes of these 4 materials. Now what we are required to do is we are required to find which of these 4 materials is the best in the forward side. Okay, how do we do that? So this means that you can see that this is what we also refer to as the knee voltage, right? In this point, If this knee voltage is as close to 0 as possible, that means we are good. Okay, or vice versa, the higher the slope of this line, the good it is. Okay, what do we know? We only know this expression. So let's assume that we are applying the same bias to that, right? And the only dependence is left is with this expression, right? The only dependence that we need to consider is this expression, right? And so here we first of all, we don't know too much about dp and lp, which is the diffusion constants and the diffusion lengths. So let's just assume that although they're not the same, for this problem they're similar. Okay, they're not changing orders of magnitude. So effectively then, the current will depend primarily on just the doping, right? Not the doping, this is Pn naught. So if you recall what Pn naught is, let me just a second, let me just clarify what do I mean. So this is P, this is N. So here the electron concentration, the whole concentration on P side, P on P will be equal to Na, 100% ionization. Similarly, P holes, sorry, electrons on P side, this will be equal to Ni square upon Na in equilibrium. Similarly, electrons on N side will be equal to Nd, the doping, and the holes on N side, P subscript N, will be equal to Ni square over Nd. And these are equilibrium numbers, so hence we also put a 0 over here. Sorry, over here. Everywhere, in fact. Okay, so what I can say now that the Js is directly proportional to Pn0 plus Np0. What is Pn0? Pn0 is Ni square over Nd plus Ni squared over Na, Np0. Nd and Na is same for all the 4 devices. This term is also irrelevant. So now Js for this problem is directly dependent on Ni squared. Okay, so the current that we have to supply is now directly dependent on Ni squared. Now if you recall the expression of Ni, or rather Ni squared, so this is Nc Nv exponent of Ni squared is this. And again, let's say you don't know anything about Nc and Nv, and we'll assume that they're similar. Okay, if they are similar, then so higher the band gap, right? The higher the band gap, the lower this value is, correct? Higher the band gap, lower this value. So what do we understand by this? We want to increase this value because we want to be as close to the ideal switch as possible, right? So we need high Js. This implies lower Eg, lower band gap. So we just need to identify the band gaps for this. So gallium nitride, gallium oxide, gallium arsenide, and aluminum nitride. I know this is 3.4 eV. I know this is 6 eV. I know this is, I want to say 1.4 eV. Gallium oxide is, just give me a second, I'll check, because I don't recall the gallium oxide band gap. It's a wide band gap semiconductor, I know that much. So let's see, gallium oxide band gap, just a second. Right, it's 4.7 to 4.9. Okay, let me just confirm with the aluminum nitride also. So aluminum nitride band gap is 6.0, 6.1. Okay, so where was I? Yeah, so this is 4.8 eV. Let's say we need as low Eg as possible, thus we'll go for the gallium arsenide. For this particular application, where we want in the forward side switch to be closer to the ideal switch, we want low Eg band gap material, which in this case among the 4 options given, which will be gallium arsenide. Very simple. So just to illustrate, it's a qualitative problem. I had taken a lot of assumptions in this. For instance, that dp and lp are similar for all the four materials, which is not the case. Definitely not the case. Na and nd are same, which is given, so that's why I skipped these two terms. The only dependence that left was on ni squared, and ni squared again will depends on nc and v. Again, I did a I was very what should I say, the extreme in the sense saying that nc and v will be similar for them. Okay, not the case, definitely not the case. So ni squared is coming out to be eg over kt, and this is just a first hand. So for instance, here I just assumed you don't know anything about the diffusion constants, the diffusion lengths, the nc and nv, right? That's how I went ahead with this problem. Let me just see whether we, because sometimes eg is still a concept which is known. Competitive exams, they can ask this question, these kinds of question directly, by the way. Just give four materials, which is the best for which application, right? Eg is something value which you should try to remember, definitely. Also ni, if you can, just try to remember. So for instance, let me just again just go for the tell you the intrinsic concentration for all these of, let's say, gallium nitride. So intrinsic concentration of gallium nitride will be about, one second, yeah. So the intrinsic concentration is, I'm not able to find. Okay, it will take a lot of time, but I request you just do this exercise yourself, because it will take a lot of time for me to figure those things out. If you still find some problems, let me know. We'll debate this in the next class, next session. Just a second. Okay, 10 to the power 18, fine. For gallium oxide, I'm talking about this, all of this at room temperature. 10 to the minus 10 to the power 18. Oh, wait, one second. Ni squared. Okay, so you're talking about ni or ni squared? Avinash, I don't okay, I feel it's just try to figure out, because this will take a lot of time for all the four materials. Silicon, because we usually, there are lot of device, in fact the majority of the devices are based on silicon semiconductors. That's why ni 10 to the power 10 per centimeter cube for silicon is well known. For others it might not be so well known. So just, if even if you cannot keep into account the ni, intrinsic concentration, please have an idea of the band gap, because band gap still can give you, while you can play a guess game in this problem. Okay, so just for the sake of completion, the answer is gallium arsenide, but we arrived at that with a lot of assumptions. Just please keep that in mind. Those assumptions are important, so if the problem changes, assumptions also change. Okay, now let's quickly go to the what's happening under the reverse bias condition. Okay, so under the reverse bias, so again, this is the without any bias, you see this wire shorted. Now we apply reverse bias. Reverse bias means now you apply now you apply positive positive of the battery to the n side of the junction. So again, as you see now, what's going to happen is VBI effectively is going to increase. So VBI will become VBI plus VR. And if you recall, the depletion width W was directly proportional to I don't remember the exact expression. It was directly dependent to VBI. So in this case, it will be VBI plus VR. Because you are applying a reverse bias, the depletion width will increase, which is qualitatively shown over here. Okay, so you can see it has increased. And just for the sake of comparison, I've also drawn what was happening in the forward bias. Forward bias means positive terminal of the battery connected to the P side. Here you can see the VBI reduces by the amount VA. So, and thus correspondingly the W, the depletion width, also reduces. You can see, I compare with the equilibrium one. Okay, and why it's not an equilibrium, you can see these two quasi-Fermi levels, EFP and EFN, in case of, so this is the reverse bias case, this is the forward. Okay, right. So how do these terms change? So the current expression, everything will remain the same as it is. If you remember, the current was Js e to the power qva over kt minus 1. This was the, so what happens in reverse bias? Va, you apply a negative number, minus 5, minus 4, minus 10. This becomes a huge negative quantity. So remember, kt by q is 26 milli electron volts. Here you are applying some volts. This will be e to the power some very negative quantity, minus 40, minus 100, something like that. E to the power negative something, a huge number, is almost 0, or at least it can be ignored in comparison to 1. So in the reverse side, J will be approximately equal to minus Js. Hence, that's what I told. This is also known as reverse saturation current density. Why this term comes? Because in the, when we apply reverse bias, only this much amount of current flows. Coincidentally, the coefficient is the same for reverse as well as the forward bias. Okay, this is happening. Why? Because in reverse bias, this goes to 0. Hence, the J reverse comes out to be approximately equal to minus Js, which is the reverse saturation current density. Okay. Okay, thanks Avinash. I'll open this link right now. Where is the, so what Avinash has shared with me, I'll also share. I mean also open here rather. So let me just do that. Yeah, so in this file you can see the materials, at least two of the materials are here, aluminum nitride and gallium nitride. So first I want you to look as the band gap energy. So here aluminum nitride is saying 6.28. It's 6 u, but that I've seen when we make our devices and we characterize them, we've seen 6 to 6.1. So let's it's fine, just an idea where it lies. Gallium nitride is 3.4 ev, which is over here. Okay, and the intrinsic carrier concentration, you can see Ni is 10 to the power minus 34 for aluminum nitride. Okay, for GaN is minus 10, 1.9, 10 to the power minus 10 at room temperature. Just to be very just to contrast this, for silicon it is 10 to the power plus 10. This number is 10 to the power plus 10. So gallium nitride is at least, is approximately 20 orders lower intrinsic carrier concentration. Okay, this is an important thing just to recall. So if you for any intrinsic device of gallium nitride, you will not get any respective amount of current, to be honest. Okay, so this, and remember in the problem that we had done, it was Ni squared, right? What we saw that the current is Ni squared, directly proportional to Ni squared. So this becomes even more severe in that case. So aluminum nitride will stand nowhere for that matter. So it will be minus 68. Gallium nitride will be minus 20. So let me also now just search for the intrinsic carrier concentration for gallium arsenide. Gallium arsenide, it is saying for gallium arsenide it is around 10 to the power 6. Okay, 10 to the power 6 per centimeter cube for gallium arsenide. So for gallium arsenide, yeah, we should be able to see that gallium arsenide is around 10 to the power 6. This is much better than gallium nitride or what do we have, aluminum nitride. Okay, the final material was gallium oxide. Yes, in our problem that we had at hand. So for gallium oxide, I hope I'm able to find, because this is usually problematic for to find in gallium oxide. I'm having some problems. Okay, I found one place, but let me see if uh, what kind of values are we getting over there? So it's not, I mean, it's just from one of the research papers, but the value they are reporting is around 10 to the power minus 23 per centimeter cube intrinsic carrier concentration. So yeah, again, so if you double that, it will minus 46. So irrespective of all that, the problem that we were sharing, that problem that we were talking about, where we had an I squared, right? In that case, still what wins is gallium arsenide, because that is 10 to the power 6. So I'm talking about this problem. So here for a gallium arsenide, this value, the Ni squared, is around 10 to the power 6. So Ni is around 10 to the power 6. So this is the band gap. So we saw that it's around 10 to the power 6. This was this was 10 to the power minus 18. So no, this was minus 23, minus 34, and minus 18. So if you square that, again gallium arsenide wins. Okay, so these are some things that the way you approach a problem, that's what my idea was. And thank you for helping me with the numbers for intrinsic carrier concentration. That's why I'm saying it's difficult to remember the carrier concentrations, much easier at least for me to remember the band gaps. Okay, now a similar concept is the junction capacitance, not a derived concept is the junction capacitance in the reverse bias. So this is a diagram of the forward bias that you're seeing. So what effectively is happening is that you have a negative charge here and a positive charge here. This is nothing but a capacitor, very similar to a capacitor. Similarly, you can write what's the capacitance. Capacitance, this is by the way per unit area. So capacitance, if you remember, is epsilon A by D. So capacitance per unit area will be epsilon by D, which is written over here. This is talking about silicon material. So this is silicon by W is the depletion width. Just put it in the numbers, is what you get. Why I added this? Because sometimes some problems may be asked in your exams and whatnot, especially for competitive exam. This is one of the problems that is asked. Okay, so just keep this in mind, that the key thing to here to recall, even if you don't recall the complete expression, but you just have to remember the W. And W, the width, we remember, if was directly proportional to the bias that we are applying, V built-in potential plus reverse bias. So hence the depletion capacitance will be, so the junction capacitance will be inversely proportional. So that's all. Okay, now coming back to the problems at hand. So the first thing is in this, for the reverse bias, what happens to semiconductor if we apply a reverse bias to the PN junction? So let's do that. So this is the unbiased on the left, and on the right you have applying a reverse bias. So what you can clearly see is that that the depletion width has increased. And why it has increased? And because of this expression, everything else will remaining the same, and this term is actually VBI plus VR. The original expression was for when it was at equilibrium. So VBI plus VR, everything else remains the same. So depletion width naturally increases. It's depicted also schematically over here, right? So if the depletion width has increased, right, so we know that the depletion width has increased. So width of depletion region increases. So this is wrong, and this is also wrong. Okay, so either B or D. Second term is we need to talk about is the peak electric field. So how is peak electric field dependent? So if you remember from our earlier discussion, peak electric field E naught or E max, the two ways of representing it. Na will not change, right, because it is still the same when you apply reverse bias or not, right? What is dependent on is xp and xn, right? And then the depletion width has increased. So if you remember, xn plus xp equal to w. If w goes up, xn and xp also go up. They are also dependent on their doping profiles, but if w independently goes up, then xn and xp will definitely go up. The ratio will remain the same because the ratio depends on nd and na. Okay, but if w goes up, xn will go up, similarly xp will go up. So both these terms will go up, right? And thus E max also increases when reverse bias is applied. Okay, Straightforward. W increases because you are now applying a reverse bias. It comes in this expression. Alternate way of seeing it is like this: when you're applying a reverse bias, so what you're doing here is you are essentially repelling the electrons, let's say which were here very near to the edge. They can still have mobile carriers. Only the depletion approximation says in the depletion region you cannot have mobile charge carriers. In this bulk region denoted in gray, you still have these electrons. When you apply a reverse bias, okay, what you are doing essentially, you are sucking away these electrons. Just think of it that way. Applying a positive bias, or let's say you are injecting some holes, these holes will be combined with these electrons, and thus this region will widen to this side. Similarly, depletion region will widen to this side. Hence you see a widened depletion region over here. Different ways of seeing this, just for to so that you can remember that. That's why I'm choosing this way. Okay, so depletion width will increase and correspondingly Emax will increase because the depletion widths on N side as well as on P side will increase. Okay, so this completes this problem. So these two are also wrong. Menu to peak electric field increases, so option D is the correct one. Emax increases as well as W increases. Okay, right. So this is a similar problem now that earlier. So there we are talking about in the forward bias mode. Okay, so this is I versus V. Again, let me draw the ideal switch first. This is our ideal switch in blue. Ideal switch, and our diode looks something like this. In this problem, we are concerned about off state. Okay, again 4 materials, PN and doping are the same side. We are required to find good off state characteristics. What does that mean? Is that it should have very low off state current. Very low off state current. That means, that's what I'm saying. This looks similar to a switch, but only under certain conditions. So in the reverse, let's now focus only on the reverse bias. Reverse bias because voltage is towards the negative side. So which of these materials is good for us? Okay, right. How do we do that? Again, same expression. This is the current that will be flowing is just the reverse saturation current, which is this expression. Again, I'll say I do not know anything about DP and LP, so I'll assume that for germanium, for gallium oxide, for gallium arsenide, and silicon, DP, their D and L are same. Okay, and also their dopings are the same. So Na and Nd are the same for all the 4 materials. Okay, so what we'll get, Js will now is directly dependent on Pn naught and P naught, and we had already seen what is Pn naught and Np naught. I'll try it again, say it again for better clarity. This is P, this is N. Holes on P side, P denotes holes concentration, subscript denotes which side you are on. Holes on P side will be equal to the acceptor concentration. Electrons on P side, N subscript P, will be equal to Ni squared over Na. Similarly, N on N side, electrons on N side will be equal to Nd, and holes P subscript N will be equal to Ni square over Nd. We put another 0 here to denote that these are at equilibrium. This 0 denotes this thing expression is at equilibrium, because remember, we are also injecting, we are applying a forward bias or reverse bias. So let's put these numbers. Pn naught is nothing but Ni square upon Nd. Np naught is Ni square over Na. Nd and Na is same for all of them. See, for all these 4 materials it's the same. So Js, we have again directly proportional to Ni squared. Okay, and if you recall from the we just need to now remember the value of Ni squared. Even if you do not remember, it's NC NV e to the power minus eg over kt. Even if you just recall the eg, we'll be fine. So for gallium oxide we saw was around 4.8 ev, gallium arsenide was 1.4 ev, silicon we know is 1.1 ev, and germanium I believe is 0.7 ev. So you can see that we want to reduce Js in off state. How you reduce? Increase Eg. So higher the band gap, because we want to reduce the off state leakage, we want to reduce the value of Js, the reverse saturation current density. We can do that if we increase the value of Eg, the band gap. And we can, among these four materials, the highest band gap that we know is of gallium oxide. This means choose gallium oxide. Among these four materials, the best is gallium oxide. If you know the value of Ni, so for instance, gallium oxide, if you remember, was 10 to the power minus 23, gallium arsenide was 10 to the power 6, silicon is 10 to the power 10, germanium will be even higher. So again, for the forward bias in this case, germanium would be the best because it has the lowest band gap. Okay, so this is the trade-off that we do. If you choose a lower band gap, right? If you choose a lower band gap material, you can get good on-state characteristics. But you'll get bad off-state characteristics. That is the trade-off that we have to pay. So we always choose a material depending on our application. In some we might need, we don't care so much about the off-state. Then we choose a material with low band gap because we want to be here. We want forward characteristics to be as close to the ideal switch. In some cases we want good reverse characteristics. In that we choose a material with slightly higher band gap. So for instance, gallium oxide or gallium nitride. This is a trade-off. The research or even in the industry, this is a trade-off that we have to live with. There's no wonder material as such. Right? Okay, so how much time do we have left? Okay, 1 minute. So this will be the last problem for today. So in this problem, what we are saying is that for very large forward bias, the current rolls off. That means the current is not as large at a given voltage as the ideal diode equation would predict. So what is the ideal diode equation? It's J equal to Js QVA over KT. What it means here is something like this: I versus V. So what I'm drawing now only in the forward side. Let's forget about the reverse side. So on the forward side, you expect something like this, exponential rise. However, what you actually get is something like this. So you see, at any given voltage, at let's say at high enough voltage, this, let's say V0, at V0 you are expecting I0 current. This is based on the ideal diode expression. What actually you got was I0 prime. So clearly I0 prime is less than I0. This means current measured is less than ideal current or predicted current. Why is that happening? That is happening because, remember, in the PN junction, I've been talking, these are the quasi-neutral regions, these two. And remember, this is forward bias is applied, some VA, right? These are the quasi-neutral regions. I've been talking about them, but these have been not playing any role. But if you apply high enough bias, what's going to happen? Some voltage starts dropping here itself in these regions. So let's say you are applying small VA equal to 1 volts. that can let's say yeah, VA equal to 1 volts, that can all of it go to VBI minus VA. So this means all of it drops across depletion region. But let's say you apply VA equal to 5 volts, then this V effective that you have, sum of 5 volts will drop across quasi neutral region. Even though you're applying 5 volts, this 5 volts is not reaching at this at I'll use a different color, just a second. VA is essentially the voltage that is being reached here, right? When you apply a very high voltage at the battery itself, right, not all of it will reach across the depletion region. Some of it will get dropped in these two quasi neutral regions, and thus you'll get, so you'll say, okay, I'm applying 5 volts, so I put Q into 5 over KT. No, you're all here, it's only reaching 1 volts, so you have to put 1, and hence you'll see a reduced current. You're in the formula you're putting 5, but actually device is seeing only 1 volts across the depletion region, and hence for high currents the voltage drops across NNP regions, these two regions, the bulk regions. So only a portion of applied voltage actually gets to PN junction. This is junction, the action is happening here, and forward biases it. So this is the correct option. So essentially what is happening here, these start acting as the resistors themselves. There are a whole lot of problems that come into the picture. These are the primary things. All right, so I'll pause here. We are out of time and out of questions as well. So thank you for listening, thank you for staying back. I'll upload this session on my YouTube channel. Of the links, I have the link which I'm sharing now in the chat box, as well as my email ID. Thank you for helping with the some person asked a doubt, pointing out the problem, that one answer was wrong in the assignment. I'll flag it to the course teaching assistants, as well as thank you for helping me with the chart of the intrinsic error concentrations. So that really enhanced the discussion. I'll stay back for a couple more minutes in case you have any doubts or comments. Feel free to ask. Otherwise, we'll wrap our session today.
Thank you so much. There are some more problems whose answers are found to differ from the options.
Okay, I then, if this is not a standalone thing, this is, you're talking only of assignment 3.
Yes, only assignments.
Okay, I request you to just compile an email in the discussion, just drop it in the discussion forum that
Yes.
you are facing such a problem. At my level, I'll talk to the course TAs and tell them, if you can tell me that whether other people are also facing this problem, because
Now I'll find out and I'll send a mail to you.
no, just you can drop in the discussion forum itself, because that way
Okay.
more people who
Okay.
have encountered this problem can also say, okay, this is a problem. The TAs will have to definitely appreciate your concerns and address them as soon as possible. From my side, I'll ask them, if they still insist that no, the solutions are correct, then you write it to me, okay, and then we discuss in the next session, okay.
Sure. Sure.
And
Thank you. Thank you so much.
and that is true for other problems as well. If you feel that you have encountered a problem in your respective colleges, universities, wherever you are, if you feel that needs to be discussed, drop an email and I'll try to incorporate in the next session.
Sure.
Okay.
Thank you.
Okay, and thank you all. I'll close this session. Thank you for staying back. Have a good evening.